Hello everyone. Today we are going to see the simulation of Droop control inverters for a standalone microgrid application. Droop control is the one of the first and fundamental control technique developed for the grid forming inverters. Here we have considered two inverters that are of same ratings and therefore they have the same droop coefficient also. And here we will analyze the parallel operation for the droop control inverters. So let us see the schematic, electrical schematic for this droop control inverter. So this is the block diagram of Droop control voltage source inverter. So here we can see this, we are sensing the current through the filters. We have used the LCL filter, the inner current and outer current of this filter. And this Droop controller generating this voltage reference and then we have used this dual loop voltage and current controller to have better control at the output of inverter. So finally, this current controller provides this voltage reference modulating signal to the PWM generator, and this PWM generator give the PWM pulses to the inverter. So now if you see the block diagram of group controller, and then we can say that this is the output current and output voltage of this converter, and then we are calculating the active and active power, and we have used this first order low pass filter to calculate the average active and active power, and then we have used this droop coefficient to get the final reference frequency and voltage magnitude for this inverter. And if you see Droop equations comes from the power flow theory, and this reference voltage set by the Droop controller according to these equations. Here NP and MP are the active power frequency and reactive power voltage Droop coefficient respectively. So now coming to the simulation. So this is the schematic of whole the means how this we are analyzing this parallel operation of Droop control based voltage source inverter. So So we are having two voltage source DC voltage sources, and this then we have voltage source inverter, and then we are have measurement. We have this measurement bus, and then we have this distribution line, and finally we have this load bus. Here these two loads are connected, and here we have used this three-phase breaker that is used to create the load disturbance. And from here we will analyze what are the effects on the controller why by providing this load disturbance. And this is the simulation result we will see at the end, and we have all written all the variables that we have used in the simulation in this MATLAB script file. So all the variables that we have used in this simulation we have written in this MATLAB script file. So switching frequency, sampling time, DC link voltage, nominal frequency, angular frequency, line to line voltage, line to neutral voltage, maximum phase voltage that we used for generating the droop coefficient, what is the rated inverter power. From here we will find this droop coefficient. If this inverter rating becomes different, this droop coefficient also becomes changed. Accordingly, they will share the power. And then we have the filter parameters and how we got this current controller and voltage controller values. They are all written over here. This current control is this fastest control, and then we have voltage controller, and here we have written this line parameters. Now coming to this simulation. So this is the DC link voltage. We have set this amplitude as VDC, and now and this is the line parameters. We have set R line 1, L line 1. We have set both this line as of same value. If you change this value, then it has impact on reactive power sharing. That is one of the major challenge for group control inverters. And we have this load. One load is of 12 kilowatt and 2 kVAR. Another load is of 8 kilowatt and 2 kVAR. So let us go inside this voltage source inverter. So here we have the first one. We have used this universal bridge to just to emulate this three-phase inverter, and then we have this LCL filter whose values are given as RC, LC for this converter side inductance. Here we have used this parasitic resistance also, and then we have RD and CF capacitance filter and this damping resistor that is set as RD and CF, and this load side inductance is set as LG and parasitic resisting set as RG. So now come to this Droop controller. So Droop control provides this voltage difference to the inverter. So here we can see this power is measured and then it is converted into average form by using this low pass filter, and it is passing through Droop coefficient, and it is taken from the reference of from the nominal frequency, and we have taken the maximum of voltage amplitude. To get the nominal voltage we have set 1 point, we have set 5% more than nominal voltage to get the nominal voltage at the LVAC base after getting drop from the line impedance. So we got this voltage amplitude difference and angular frequency difference, and then it is sent to this voltage controller to have this dual loop voltage current controller is used to have better control at the inverter output. So this voltage control works in DQ reference frame. So we need to convert this voltage amplitude into D axis component. So we have multiplied with a square root of 2, and to convert this omega into omega 2 we have used the integrator. So now this is the voltage controller block diagram. So here we have used according to this block diagram, whatever we have shown over here we have used accordingly, and we have used this 2 pi controller in which both the proportional and integral coefficient are set as kpv and kiv respectively, and for this pi controller also this proportional and integral coefficient are set as these values, and we have this filter capacitor is taken here to get the uh, final current difference in the DQ components, and this current reference in DQ components we will provide to this current controller, and in the current controller this schematic looks like this. Here we have used this filter at the inductance value, the filter used at the output of converter, and here we have again 2 pi controller whose these proportional integral coefficient are set as kpi and kii respectively. So finally we are converting, this will provide this voltage reference frame in the DQ components. So this DQ components we again need to convert this, we need to convert into natural reference frame. So after getting this modulating signal in ABC reference frame or natural reference frame, we will provide to this PWM generator after getting uh, divided by this VDC upon 2. So this will provide the PWM pulses to this three-phase inverter, and that will final establish the voltage output at the converter side, at the converter out. So we have seen this how the symmetric looks inside for voltage source converter, and inside also we have seen all these blocks. Now we will see the simulation result. I have already run this model. So if you see this simulation, so this is the voltage that we are getting at the output of converter. So here we can see that when we are providing this voltage disturbance at t equal 2.5 second, this voltage magnitude little bit got decreased due to increase in the power output, and this is the RMS value of voltage that we are getting at this load bus. So we are getting 232, that is approximately equal to the nominal voltage. So this is the RMS voltage magnitude. So here you can see the drop in this RMS magnitude after increasing this power demand, and here we have this frequency at the load bus. So since in Droop control we have a steady state errors, so therefore they are not there. Whatever the reference you will provide, there will some drop at the output of the converter. So we have the reference of 50 hertz, but but it works on this Droop control theory. So there will some deviation from this nominal frequency as it delivers power output. So initially it is having 49.85 hertz, and on increasing this power demand at the load bus, it again drops to some value, and again after disconnecting the load, it regains this magnitude of 49.85 hertz. So this is the current sharing from the both converters. Both uh, both inverters are sharing current, and they are in synchronization. And this is the voltage that we are getting from both the converters, and both are synchronized and both are overlapped to each other. And this is the load current. So load current from a converter, from the first converter, I think, yes, from the first converter. So on increasing the load demand, this increases the power output, this increases the current output, and this is the power sharing from the both converters. That is the most important, because this group controls fundamentally that they operate in parallels, and they share power without an external control. So they are decentralized control, and they share power according to the Droop coefficients, and Droop coefficients comes from their power converter rating. So here we can see this both converters share power equally because both are of same ratings. So red one comes from this first inverter, and green curve shows for the second inverter, and the reactive power also you can see. Initially they are sharing, they are delivering power of 6 kilowatt and 1 kilowatt, because initially they are having total load of 12 kilowatt and 2 kVR, and when we have increased active power to 8 kilowatt, they have increased their active power output by 4 kilowatt, and this reactive power also got increased because we have increased the reactive power demand also. So that's all for today. Thank you. If you have any doubt, you can ask in the comment box. Thank you.